Yeah, that's what I saw. I only saw.
Okay, so what do you think? How are we going to do something like this? We got to, well, what does this mean, first of all?
You can go through what we call absolute value.
Okay, it's an absolute value, right? Definite integral means we're looking for an area under a curve. Okay, so there's a couple ways you could look at this. We could look at this one geometrically, honestly, but let's look at it both ways. So if we wanted to come up with a simple graph of this, what does the graph of the absolute value of 2x minus 1 look like? It's going to be a V. Good. It's going to be a V. And where is the vertex of the V?
0, -1.
It's 0.
What? It can be negative though, because it's absolute value.
Right. So it's at 1/2, isn't it? Right. How do we know? We have an absolute value function.
If it's 0, it's.
Okay, we could find out where it equals 0. We know that an absolute value function has to look like a V that's bouncing off the x-axis, right?
Yeah.
So we know that the 0 of that function is at 1/2. So right here is going to be the 0. Now what's the right leg going to look like?
That's straight line.
Okay, with a slope of 2. All right, so we're going to rise by 2 and run by 1. Agreed? So it's just going to do something like that, right? Left leg,
It's just the same thing.
-2, right? So we'd rise by 2 and run by -1, so it's going to look like that. And we're looking for the area under the curve from 2 to 0, and so we're just looking for the area of that triangle and that triangle, right? So we ought to be able to add those up manually, right? But there should be a better way to do it too, and I want to deal with absolute value functions analytically, so everybody's get pulled away with it, so we can really focus on it. So what's going to be the area of that little triangle there? Half. Well, that's 1 and that's 2.
So 1/2 times 1.
Yeah. So what is that? 1/4. Okay, so we get 1/4 from this guy, and then how about this guy here? Yeah, it's going to go up to, what's the height going to be? Let's see, we're going to go up to 3, I guess, is that right?
Yeah.
Okay, so it's got a,
3/2 times 3.
So 4.5 times 1/2.
so 1.5, so it's going to, yeah, it's going to be 3/2 times 3 times 1/2. So 3/2 times 3/2, 9/4. We add those up, 1/4 plus 9/4 is 10/4, so 5/2. Okay, so the total area equals 5/2. How could we get that without having to draw a picture? You know, because it wouldn't work if it were curvy, right? The fact that those are straight lines define the function makes it easy to add up geometrically, but it may not be that way in the future, right? So how could we come up with a way to deal with this analytically, right, algebraically? So what are we going to get? So what do you think? How can we define that absolute value function in a way that we can deal with it using analysis?
Take an integral.
Well, we're going to take an integral, but it's hard to take an integral of an absolute value function because we don't have a standard form for that, right? What can we do with an absolute value function, though? Can we rewrite it in a way that's going to make it amenable to stuff we do know how to do? Yeah, what is the definition of absolute value of A?
Square root of A squared.
Well, okay, yeah, but that's going to make it pretty difficult. Is there a way we can write this? Okay, it equals A when?
A when A is greater than 0.
Okay, so there's one thing. It equals A when A is greater than 0. What else?
A when A is less than 0.
Well, no,
Equals negative A. when
negative
it's less
A
Okay.
when A is less than 0. We gotta make it positive, right? And then it equals 0 when A equals 0, right? Now that we can handle, that's a piecewise function, right? Each individual piece is easy to deal with, right? So that's our strategy here. We wanna be able to write the absolute value function in the integrand. We wanna be able to write that as a piecewise function, and then it'll make sense. You'll see. I mean, if we can write it using simple pieces on parts of the domain, we're doing a definite integral, and so we can split the definite integral up into different areas and just add up the areas like we did here, right? So absolute value of 2x minus 1 equals what?
No, yeah, yes.
2x minus
Good. When?
1, x is
When- Well, okay, when 2x minus 1 is greater than 0, but we can write that in terms of x, right? So if 2x minus 1 is greater than 0, solve for x.
1/2.
X is greater than 1/2. Okay, good. So when x is greater than 1/2, it equals the opposite of 2x minus 1, which is what? Negative 2x. I mean, I can just do this, right, if I wanted. When x is what? And it equals 0 when x equals 1/2, right? Okay, so then that helps. Right now we should be able to set up this integral in a way where we can add up the areas individually, right? We're going from 0 to 2. Okay, so what's this going to look like? Let me go to the next page. We're getting too crowded here. So there's our definition. Yeah. So we can write the integral from 0 to 2 of the absolute value of 2x minus 1 as what? Based on our piecewise function. We're going to write the piecewise function. We're going to write the absolute value as a piecewise function. So the area from 0 to 2, I'd have to break it up into pieces, wouldn't I?
Is it going to be the 0 when x equals 1/2, and then the top one, 2x minus 1, and then x is greater than 1/2?
When x is greater than 1/2.
We're going to use both of those?
Say it again.
We're going to use both of those?
Yeah, we're going to, aren't we? Because look, our integral goes from 0 to 2. Well, this top function only starts to survive when x is greater than 1/2. It's at 1/2 that it makes that transition, right? So what do you think? We know what the area looks like, don't we? Looks like that. How do we add up that area? Okay, 0 to 1/2, what are we adding up?
Negative 2x minus
Ah, it's that one, isn't it? Right, that's the piece of the function that on the interval from 0 to 1/2. So we're looking at the area under that part of the function on its domain, right? So we're going to get the integral of of negative 2x minus 1. Well, what is that if I distribute it? From 0 to 1/2, good, plus the integral of 2x minus 1 from 1/2 to 2, right? And those aren't hard. From there, it's no big deal, right? We can use the first fundamental theorem. It's no big deal. But I just wanted you to see how to deal with an absolute value function. Okay. All right, next issue. I want to show you one other thing. What about, okay, what if we want to do something like, I've got a function.
Yeah, first.
And here's my function. Okay, I want to find the average value of the function on the interval from A to B. Suggestions. Averages are tricky things. They mean, there's different ways to define averages, right? You can define an average as a median. You can define it as a mean. You can talk about a geometric average where, for a geometric average, we would say that the geometric average of 2 and 8 is 4, because 4 over 2 equals 8 over 4, right? There's different ways to define averages. But in this way, we mean what's the most likely value of the function between A and B.
Can you break it up into segments, like an infinite number or like a large
I mean, we could, but we actually can, we know how to add up an area, right? What do you think? Here's another way to think about this. Let's say that this function here, instead of just being f, let's say that this function is velocity. And this is time. What's the area under a velocity time graph look like? Going back to kinematics. Physics studies.
Is that the amount of distance
Well,
traveled?
it's displacement,
Yeah.
right? The area under a velocity time graph is displacement, okay? So describe the motion from time A to time B. What's the motion of this car doing? What, he's accelerating, isn't he? So he starts at a low velocity, and he's picking up velocity, so he's accelerating. Now he's starting to ease off, and at the very end, it looks like maybe he actually decelerates a tiny bit, but his speed is pretty high, right? Okay? So how could we define that in terms of an average velocity?
Maybe like do what you would say.
Take the average of the values at A, and we're getting somewhere. Take the average of the value at A and the average of the value at B. Okay, but what if my profile looked a little different? It's a good idea. It's a good start. But what if my velocity time profile looked like this? I'm going to try to find ways to mess up your suggestion. That's a good suggestion. So what if it looked like this? Okay, so there's the value at B, there's the value at A. Does it make sense that for this one, the average of those two looks like it's about right there? Does that seem like a good value for the average velocity?
Yeah.
It does?
No.
No.
I mean, maybe it does. It doesn't to me. See, what seems wrong with that average velocity?
Too high.
Seems too high, doesn't it? Because most of the time he was traveling at a low velocity, and at the end he just spiked at the very end, right? Okay, so back up to this picture. Can you think of a way to define what an average velocity might be? Now think about different scenarios. In this scenario, the person is stepping on the gas and taking his foot off the gas up here maybe, right? But he's traveling some distance. It's all positive, so we'll call it distance. It's really displacement, but he's moving in the positive direction the whole time, right? He's traveling some displacement, some distance away from where he started, defined by the area under this curve.
Could we do something with using the distance divided by time?
The distance, okay, kind of, but I mean, now think about a different way he could travel the same distance. Describe a different way that might define average velocity. See, this time, put his foot down on the pedal and he's speeding up, takes his foot off the pedal and he starts to slow down and coast. Is there a different way that he could have covered that same distance defined by that area that might better describe something that we could call like an average velocity?
Like line of best fit?
Oh, well, I mean, yeah, possibly line of best fit, but even the line of best fit would mean acceleration, wouldn't it? The line of best fit, it's not a bad idea.
Could we
Like here, maybe this is the line of best fit on our interval, something like that.
could we have another function that has the same exact amount of area,
Oh, okay, so,
but
and that's.
it's gonna be flat?
Okay, how about that? What if we did instead, what if we picked another function, a constant function that had the same area? So that would look, instead of looking like this, it would look something like this, right? So I don't know where exactly it would be, but maybe like right about there. From A to B. Describe what that trip would be like.
Just traveling at constant speed.
Yeah, cruise control's on, right? Traveling at a constant speed, and what specific speed could we call that? The average, right? It's the average. And why is it the average? Because that's the speed we'd have to travel to cover the same amount of distance over this time interval that we did using our accelerated path. Right? Does that make sense? Okay? So that is what we call the mean value of the function, right? But how do we get that? Now let's think about what we just did here. So we've got just fix this a little bit. It's right about there. So, okay, those two areas, we're defining them to be the same, right? The unknown here is the value of the speed that we set the cruise control on, right? So we could call that our mean value. Okay, so we could call that, if we wanted to, they don't use C in it, do they? So, yeah, they do use C. Okay, so we could call this, for example, let's just call it f of C. And f of C equals the mean value of f of x on interval from A to B. Okay, how could we set up an equation to solve for f of C? The areas have to be equal, don't they? Right? The purple area and the blue area have to be equal.
So set up integrals.
Okay, so we could maybe try to set up, let's try to set up some equations that represent there we go. Some equations that represent the areas. What's an equation for the blue area from A to B? Or an expression, not an equation. How do we do that? That's what we've been practicing, right? This is just the function f of x.
The integral. Take the integral.
Okay. Oops, wrong color. F of x, or we called it v in this case, but let's just call it f, right? F could mean velocity if we wanted to. So the area under the blue curve is the integral of what?
A to B.
From A to B of f of x dx, right? Okay, how do we say the purple area?
A to B.
Okay, we could use an integral, but that's a geometric area. We gotta be able to not have to get so fancy with that
Delta
one.
X.
Okay, delta x
B
is
minus-
just b minus
B
a,
minus A.
isn't it? Right? So we get b minus a times, well, whatever that is, right? F of c. That's what we're trying to find. Well, that's a pretty easy equation to solve. What's f of c equal to then?
F of C is equal to F of X.
Yeah, but if I solve for that,
Then the integral divided by b minus a.
yeah, we just get f of c equals this area divided by the width of the interval, right, by b minus a, okay? That's it, right? That's all we have to do to find the average value of an interval, of a function on an interval. All we have to do is divide the area of the function by the width of the interval, okay? So what, does that make sense? What does that accomplish? I mean, you can think about it in terms of these pictures, and I think that's helpful, right? And the context we used, I think, is a good one. You know, we used a car that's changing its speed and covering the same distance as it would have if it had had its cruise control on at a specific average speed, right? Okay, there's another way we could kind of think about this geometrically. We could say, and bear with me on this, let's say that we've got these walls, we're in this two-dimensional space, and we've got these walls that define our partition, our interval, right, over which we're trying to find an average value. Well, let's bring out we'll get this to Acme Store again. This is a two-dimensional angle grinder, and I'm just going to grind down my function into rubble from the top on down, right? I'm just going to keep going until the rubble that, when I grind this function down, the rubble that I create fills in the divot so we get a flat function, right? Would you agree that if I did that, if I brought in my angle grinder and I start grinding, it's just going to stay contained in these walls, right? That this area right here, all this rubble up here, is going to exactly fill in that divot, right? And beyond that point, I can keep grinding, but it doesn't matter. The rubble's just going to stay the same shape, isn't it? Right? So we're just reconfiguring the area, in other words. We could reconfigure this area. We could morph it from a curvy profile into a flat profile. And if we do that, the height of that rectangle that we create defines our average value. Okay? Make sense? Okay, that's a good definition of an average value. And that is, so technically what we just said right here, this is, that is the definition of, what do we call this? It's actually, this is a little bit different. This is what we call the definition of the average value. Definition of mean value of a function on an interval. Technically, if you look in a textbook, that's how we define the mean value. And then the mean value theorem looks a little different. The mean value theorem just says that the integral of f of x dx from a to b equals f of c times b minus a. So all we did was we just stopped right there. We didn't solve for f of c. We just wrote the areas being equal to each other. That's what we call the mean value theorem. For integrals, for definite integrals. They mean exactly the same thing. I mean, I think it's silly to even call them different things. They mean it's exactly the same relationship, isn't it? Okay? So let's look at a problem like you're going to see. So what if we, let's see, we've got. Like this. How are we gonna do that? Okay, so the integral of this function from 1 to 4 defines the area, right? We'll just call this f of c. Now what? Divided by 3. Or if I want to, I could even just put the 1/3 out front. Either way, it doesn't matter. Okay, so what's that going to give me? What is this integral? Let's practice doing a definite integral. What's the antiderivative of 3x squared?
X cubed.
Okay. Minus. Okay, but there's no plus c here, right, because we're doing a definite integral. So we're just going to evaluate this from 1 to 4, right? So we got some choices now, and this is, we need a little practice with this stuff. So we could write this as, one way to do this would be to say 1/3 times this whole thing evaluated at 4, which is going to be what? 4 cubed is 64, good, minus 16, 48, minus this whole thing evaluated at 1 is 0. So we're going to get 1/3 times 48 is what? 16, right? So if that works. Or if we want to, we could split this up, and I want you to see this, we could split this up into pieces, right? We could evaluate this integral from 1 to 4, but when we do the definite integral, we could write it out this way. We could say 1/3 times x cubed from 1 to 4 minus x squared from 1 to 4. Of course, I'm going to get the same answer. What's this going to give me? It's going to give me 1/3 times, let's see if we just plug the numbers in. What's this one going to be? 4 cubed minus 1 cubed is, what was that? 63?
63.
Minus 4 squared minus 1 squared is 15, okay. Well, 63 minus 15 is 48, right? Which is also 16. So take your pick, right? I just wanted, I mean, I'd probably just do it this way, you know. But you can, if I have a bunch of terms, I can if I want to. I could, instead of evaluating the whole thing from 1 to 4, I could just do it term by term from 1 to 4 and then add up the contributions. Okay, make sense? Okay, so now there's one other thing we could ask about this though. We could also say, okay, find the average value, but maybe I also want to know where does f of x have its average value? Okay, so where's that gonna be the case?
Or-
Three x squared.
Ah, okay, so, yeah, so now all I've gotta do is I've gotta ask, when does the function have the value of 16, right? Okay, so this part right here, if we go to the next page, you guys have that written down, right? What was f of x again?
3x squared minus 2x.
Okay, and we found that f of c equals 16. Well, then think what we're doing. If f of c equals 16, that's just like saying 3c squared minus 2c equals 16. Solve for c. What would I do to solve for c there? If I could factor, but what do I have to do probably first?
Put the 16 on the other side.
Okay, I gotta put it in standard form, right? So I'm gonna get 3c squared minus 2c minus 16 equals 0. Yeah, is that gonna factor? Actually, it will, won't it?
Yeah.
6 and 8.
Negative 48, yeah, it's gonna factor, isn't it? So we could do, we know that the only, if it factors conveniently, we know that we've gotta have a 3c and a c. That's the only factors of 3 are 1 and 3, right? Convenient factors. If it doesn't factor, we'll just use quadratic formula, right? Now, what are the factors of negative 16? Well, we could have,
It's just gonna be 6 and 8.
yeah, we could have, I mean, we could do negative 4 and 4, we could do negative, so we could do, let's try this. So negative 6 and, oh, sorry, the factors, yeah, the factors of 16 though, what are those gonna be?
You can just multiply 16 by 3 and then divide in the end.
Right, so, I mean, you're saying go bottoms up. We can do bottoms up, that's fine. So bottoms up is where we're gonna say AC equals what? A times C is, you guys remember bottoms up?
Yeah.
So negative 48, B is negative 2. Numbers that multiply to AC and add to B are negative 8 and positive 6, right? So we get magic numbers. Right? And so then with bottoms up, remember what we did, right? We just said we're going to start with x minus 8 times x plus 6. But what do we have to divide each of the magic numbers by? By 3. Good. And so we end up with, when we go bottoms up, we get 3x minus 8 and x plus 2, right? Okay. The other way you could do this one, if you want to take the time to do bottoms up, I'll just show you another quick way to think about this, is you could say, you could demo out, because there's only one possible combination of factors of 3. There are quite a few possible combinations of factors of 16, but we can probably narrow it down pretty quick. What are they? Well, we could, obviously it's not going to be 16 and 1, right? So we could do negative 8 and positive 2. We could do negative 4 and positive 4, positive 4 and negative 4, 8 and negative 2. We could flip those around. Do any of those give us the right cross terms? So we get, let's see, those work, don't they? Right? If I did 3c plus 8 and c minus 2, if I were to FOIL that out, doesn't that work? We're going to get negative 6c, actually these are the ones that work, aren't they? Right here. Yeah, these guys. I'm going to get, if I FOIL this out, I'm going to get 3c times 2 is 6c minus 8c is negative 2c, right? If I FOIL that out, so let's just show that that works. 3c minus 8 times c plus 2. If I FOIL that out, I'm going to get 3c squared plus 6c minus 8c minus 16. So that works, doesn't it? Right? See what I'm saying? So you can always just, this, honestly, this one wouldn't be a great one to do. There's too many possibilities. But if that had been like a 6 or a 10 or something, where there are only just a couple different factors, of C, and there's only one combination for A, it's usually, I think it's quicker just to do this, just by kind of guess and check, trial and error. Just look at all the possibilities, you can check them in, 30 seconds, and then if it doesn't work, you just move on and quadratic formula or something like that, right? Okay, so we got our answers though. Our answers are from over here or over there. What are our answers? Either x equals, and I wouldn't even had to do this, would I? I could have just gone right from here. Either x equals 8/3 or x equals -2, right? So those are our two values. Well, on our original problem, which of those are in the interval from 1 to 4?
8/3.
8/3, right? So 8/3 is, and so what did we just find? Well, we just found then that that's the value of C where the function has its average. If we go back to look at our picture back here, how would I draw C then? What is C? That's it right there, isn't it? Right? It's the value of x where the average, the average value of the function crosses the function. And there might be multiple ones, right? Does that make sense though? So that's why we called this, you might have wondered, why the heck did we call this f of c? What the heck is c? That's c. C is the x value where the function has its average. Okay? It's a lot of stuff. Okay? That's a lot of stuff, but when you do these problems, you'll see they're not very hard. But there's, I wanted to give you the background. Okay. Whew. That's a lot of work. Why don't you guys just take a week off?